We're very happy to have Alex Kontorovich, who will talk about Polyhedra, Hyperbolic 3-Manifolds, and Arithmetic.
Okay, so thanks very much to the organizers for the invitation and the opportunity to speak here. So let's start sort of at the beginning. So what is a polyhedron? For me, a polyhedron is a three-connected planar graph, but that definition is actually a theorem of Steinitz from about 100 years ago. So I'm interested in these. I'll come back to this first point that Thurston sort of explained a way to attach a three-manifold to a polyhedron. Let's work our way there. So everyone knows what this is a three. So it's a planar graph. Three connected means if you remove two edges, it's still connected. If you can remove any at most two edges, it's still connected. Three edges, of course, you can make it disconnected if you take out. But everyone can see what this is. It's a tetrahedron, obviously. Okay. So this one's a little less obvious. It's another three connected planar graph. It's a triangular prism, exactly right. So you just stand these things up and you get a triangular prism. Okay. So this map, this idea where you take the abstract vertices and edges and realize the vertices in space so that the faces lie in flat planes and the edges are all straight lines is called geometrization. Okay. And now there's lots of different geometrizations. So here's another geometrization. I just made the triangular prism a little bit taller. And some geometrizations have what's called a midsphere. So imagine just blowing up a sphere from inside the polyhedron until it hits the edges. And then you can't blow it up anymore. And this midsphere, it hits some edges, and I can't make it any bigger, but it's not tangent to all the edges. Whereas in this other geometrization, when I blow up a midsphere, it just perfectly kisses every single edge. Okay, so we're interested in this configuration where this situation where you give me some combinatorial data and there is a realization of that data geometrically so that there's a midsphere. And so the question is, for which polyhedra does there exist, for which combinatorial types of convexly realizable polyhedra, aka three connected planar graphs, does there exist geometrization with a midsphere? And the answer is very nice. It's all in 3 dimensions. In 4 dimensions, it's not true. So there are already convexly realizable polyhedra for which there is no geometrization with a midsphere. This is a theorem. Again, Thurston sort of realized the power of this theorem in the 80s, but he traced it back to work of Vinberg student Andreev. And then I don't know the exact history of this, but this is now known as the Kolbe-Andreev-Thurston theorem. So you can use ideas of Kolbe from the 30s on uniformization to prove this thing. So this is now called the Kolbe-Andreev-Thurston theorem, that you give me a combinatorial polyhedron, I will be able to produce for you a geometric geometrization so that there's a midsphere. And once you have this midsphere, you also have simultaneously geometrized the dual. Because if you just take the cone off of the midsphere, that will give you the dual polyhedron with the same midsphere. Okay, so you had the triangular prism, and now you have the triangular bipyramid as the dual that sits on top of it. So far, so good. Please interrupt at any time, ask questions. Okay. So my claim is that this now gives you a map from combinatorics to hyperbolic 3-manifolds. How do you do that? So let's look at that picture again a little bit. It's hard to see 3D, so let's try to strip away some of the things. The faces intersect the sphere at circles. So let's move everything out except the circles. And those circles we can stereographically project onto the plane so that we get something in 2D that we can actually look at. So here's that same intersection pattern just projected onto the plane where this will work. And do you still see, let me get rid of the red circles, do you still see in the blue circles the same combinatorics as the original? So if not, let me color things in a little bit. So the red triangle here is the red curvilinear triangle there. Orange is the orange quadrilateral, and so on. Every vertex corresponds to a circle, or maybe better yet, a disk, a circle with an interior. And some circles are half planes, and their interior is, the normal vector to the half plane. Okay, so vertices have turned into circles and half planes, or disks and half planes, and then the interiors are the interstices. So far, so good? So that's really what I'm after, is this kind of geometrization of combinatorial data to what we can think of as circles and lines, but it's not enough to have just the cluster of circles whose tangency graph is isomorphic to the original tangency graph. We also simultaneously want the co-cluster of circles with the dual tangency graph. And once you have both of these together, here's how you make a three-manifold. So you take the group generated by inversion in both the cluster and co-cluster, and you extend that from an action in the plane to an action in hyperbolic 3 space. This is just a standard Poincare extension. So far, so good? Let's just see that a little bit more clearly. So if we take these things and we sort of lay it back down flat, this is going to be another 3D picture, but that's a fundamental domain for the action. So you can think of these circles, instead of circles at the boundary at infinity of hyperbolic 3 space, you can think of geodesic hemispheres. And the exterior of those hemispheres is going to be this hyperbolic polyhedron, which is a fundamental domain for the action. So now I've completely told you what the map is. You take your combinatorics, you compute this group gamma acting on hyperbolic 3 space, you take the quotient. Okay. So this is a nice family of hyperbolic 3 manifolds. Yeah, so I should let me point out a few things. This manifold is all ideal. The vertices are all at infinity. It's all right angled. All the anytime two walls meet, they meet at right angles. And as a hyperbolic polyhedron, its combinatorics is that of the rectification of the original. So it's the you take your original polyhedron, think about cutting off the corners until you get all the way down to the midpoints. So the place where those meet, that's the rectification, and that's what the combinatorics of this polyhedron will be. So far, so good. I know it's a number theory seminar and we're doing a lot of geometry, so feel free to slow me down with anything. Okay.
And what was the definition of this gamma pi again?
Gamma pi. So you start with your combinatorial data, just graph, planar graph, 3 connected. You geometrize it. That geometrization is, once you unfold it into the plane, you can see it as just a configuration of circles. One configuration for the original polyhedron and another one for the dual that's sort of lying orthogonal to. You take inversions in those, acting on the upper half space model of hyperbolic 3 space.
Okay.
Inversion with respect to each circle. So
With respect to each circle.
The circles that generate.
The circles are generated,
Okay.
exactly. The circles generate, yeah, inversions through the circles, through each circle are the generators, and then this is a fundamental domain for the kind of 3 manifold you can see.
And just based on how we're embedding, these are all 3-dimensional polyhedra.
These are all 3-dimensional polyhedra, yeah. This whole story is going to be in 3 dimensions. Yeah, as I said, in 4 dimensions and higher, this map doesn't exist.
Yeah.
And so the main question I got interested in about a decade, a little bit over a decade ago is, okay, this is some process that goes from combinatorics to geometry. Is the image arithmetic? How often? What's the story with, I like arithmetic hyperbolic 3 manifolds. Do we ever get these? So, so the main question is, can we classify which combinatorial information gives rise to arithmetic in this way?
Can I ask a stupid question?
Please.
As a non-number theorist, what does it mean for the manifold to be arithmetic?
I'm gonna say that in a second. I'll give you the criterion for it, but just the definition of it is, so if you have a hyperbolic 3 manifold, there's a complicated definition, and then there's a definition that applies in this context. And let me give you the one that applies to this context. Basically, you have orthogonal groups of quadratic forms of hyperbolic signature, like signature n1. In this case, signature 3, 1, 3 positive eigenvalues, 1 negative eigenvalue. And if you start with a rational quadratic form, for example, you can do this over number fields as well. Let me just explain it over rational so I don't have to talk about different embeddings. If you start with a rational quadratic form over number field, then the set of integer points is a prototypical arithmetic group. And then something is arithmetic if it's commensurate with one of those.
It's the group that's arithmetic, not the manifold. Yes, okay.
The group is it.
Sorry, can I just try to understand? So you start with a polyhedron.
Yes.
And then you said first you put it so it's around the sphere.
Yep.
And then what does it mean to rectify it?
So you have not just the polyhedron, but also its dual at the same time.
Okay.
So both of those cut out spheres out of the ball model of hyperbolic space, if you want to look at it there.
Yeah.
And inversion through all of those cuts down to a finite volume lattice.
Can I think of this in terms of putting a hyperbolic metric on something to do with my original
Sure.
polyhedron? Like,
Yeah, you can. Another way of thinking about it is that when I had that original picture, let's see if I can go back. This is the picture, keep in mind. So the yellow ball, this mid-sphere, is the boundary of hyperbolic 3 ball in the ball model. And then in the Klein model, those straight plane cuts are that rectification is literally the fundamental region. But it doesn't preserve angles in this model, and so we're gonna move it somewhere where it does. Just for the picture, but all the information is right there. Does that answer your question?
no, but I need to think.
Okay.
So is it the intersection of the red polyhedron, the blue-green polyhedron, and the yellow sphere?
Exactly.
Yeah.
Inside the sphere.
So, and that's the fundamental domain.
That's a fundamental domain in the Klein model.
With its hyperbolic metric coming from the ball.
Yes, coming from the Klein model, yeah, of the ball. Yeah.
Okay.
So then if you want to think about just take those same circles and put geodesic hemispheres on top of them, if you prefer to think in the Poincare model, that'll have the same effect. So far, so good. Please, again, ask anytime.
Is there any understanding of the volume is going to be in terms of the combinatorial data?
Yes, because you have the Lobachevsky function that tells you volumes in terms of dihedral angles and it's yeah, you can work it out. Okay, where were we? We did the stereographic projection. This is the problem with making slides. You can't jump right back to where you were. So we have this inversion, and we got our manifold, and when is this thing arithmetic? Okay, so this is where when is this thing arithmetic? Okay, so for the triangular pyramid, triangular prism, this guy that we've been looking at, the answer is yes, it is arithmetic. That example. I have to explain to you again how to see that. We found a whole bunch of other things. In particular, I'll isolate the tetrahedron, the octahedron, and the cube octahedron. The cube octahedron itself, by the way, is a rectification of the cube. You take a cube and you cut off all the corners. But now the cube octahedron is my seed polyhedron, so it's actually the rectification of the cube octahedron, which is the fundamental domain for that guy. Lots of others are not arithmetic. For example, the dodecahedron and icosahedron. And so let's just define pi sub a to be the polyhedra which are arithmetic, which after this operation give you an arithmetic group. Okay, so there's a list of what's in there and what's not, and the classification problem is who's there. And here's the first problem if you want to do some kind of classification. Well, there's infinitely many things that are there. So what do you mean by classifying? How do we get our answer? Let me explain a little bit about the infinitude theorem. So let me give you a quick sketch. It's a very simple observation. If you have a seed polyhedron that's arithmetic, then there are certain operations that we call growths. They're more complicated than this, but some prototypical growths are like gluing along a face or a vertex. And you can do some other things that preserve the arithmeticity. So the reason the triangular prism is arithmetic is because it's the gluing of two tetrahedra across a vertex. And the tetrahedron is arithmetic. Okay, and then you can keep gluing and making arbitrarily complicated polyhedra based on the tetrahedron, and they will all be arithmetic, even though they give rise to.
What's the relation between the arithmetic groups?
They're commensurate. Basically, this operation gives commensurate groups.
Okay.
And so once you have one that's arithmetic, then the rest are. If you glued it the wrong way, if you took genuinely different polyhedra and glued it, that would be something like the Deligne-Mostow examples of non-arithmetic groups. That's in higher dimensions how they combine them, where you have something over one number field acting against another and gluing them together. Anyway, yeah, but as long as you use the same seed polyhedron when you're doing this gluing, you stay in the same commensurability class. Okay. So, okay, let's go all the way back to Roland's question. Wait a second, if you just hand me a polyhedron, what am I doing to determine whether or not it's arithmetic? So let's discuss arithmeticity. We're going to recurse back a little. So there's a beautiful criterion by Vinberg about what happens in the case of reflective groups. We have to look at a certain Gram matrix, but let's pause there for a second. Let's just talk about inversive products. So if I have two circles, C1 and C2, which are really geodesic hemispheres, you can think of them as geodesic hemispheres in hyperbolic space, then their inversive product is, well, there's some orthonormal vector connecting the two, and there's some hyperbolic distance d along that orthonormal vector, and the hyperbolic cosine of that distance is what I'll define to be the inversive product. So let's see why this is a useful definition. So far so good, that makes sense what this is. So here's a quiz. So if C1 and C2, if you think about it, has what I've drawn, the blue and the green have some distance apart. If I pull them together until they're just perfectly tangent, what happens to the distance? 0. What's cosh of 0? 1, right? So if they're tangent, then their inner product is 1. Now, what if I pull past the point where they're tangent? So then their hyperbolic distance, it goes along the real line to 0, and then once they pull inside each other, it actually becomes purely imaginary. And the cosh turns into a cosine, and then it's the familiar formula of it's the cosine of the dihedral angle. Okay, that's what happens to this inversive product. And so if C1 and C2 are actually orthogonal, then the angle at which they meet is pi over 2, and cosine of pi over 2 is 0. Okay, so the orthogonality is measured in this nice way. If I keep pulling them until they become internally tangent, or if I just take a circle inner product itself, so that's like going from pi over 2 all the way to pi, and cosine of pi is -1. Okay, so these are the three things I want you to keep in mind about these inversive products. If tangency is measured by 1, orthogonality by 0, and self-intersection is negative. And let's see how we can build up the Gram matrix of all of the inversive products of the circles in this geometrization. So the first thing to remember is that we had 6 vertices in the triangular prism and 5 vertices in its dual, this triangular bipyramid. And so we're going to have 6 plus 5, an 11 by 11 matrix. And the first thing I'm going to do is just record that there's -1s down to that. Self-intersections are -1. And then if I number these, so this is number 1, 2, 3, 4, 5, 6, the blue walls, then I can already record the inner products based on tangency. So 1 is tangent to 2 and 3 and 6. 1 and 6 are tangent at infinity. And so we should see that here. 1 is tangent to 2 and 3, not 4, 5, and 6. And so on. And this is this little 6 by 6 submatrix is recording the tangency data of the original triangular prism. Similarly, the other walls we'll call 7 through 11. And here's the information. They're almost all tangent. The only ones that aren't tangent are 7 and 11 are not tangent. Okay, so that's all the ones in this block. And then some of the walls are going to be orthogonal to other walls. So we can record all of that information. Like 1 is orthogonal to 7, 9, and 10. So in row 1, I should see zeros in the 7th, 9th, and 10th place. Okay. All of that information is purely combinatorial, given from the original data of the polyhedron. And so here comes the Kobe-Andreev-Thurston theorem. It's that all of the other unknown dots can be filled in. There is some realization of these spheres so that all these other dots can be filled in. The question is, what filled in with what? What goes there? So in the case of this triangular bipyramid, they're filled in with 3s, 4s, and 2s, and 7s. Now this is weird. It shouldn't be like this, because remember what it's measuring. The fact that 2 and 5 have an inversive product of 3 means that this wall 2, this circle, this geodesic hemisphere above circle 2 and circle 5, have hyperbolic distance at this transcendental number 1.762, which is the arc cosh of a whole number. So it's really weird that these things are coming out to be integers, but they are. Okay. So here's Vinberg criterion. So here's, if you didn't like my definition of an arithmetic group, you can take this to be the definition, even though it's a theorem. So if you look at this Gram matrix, Gij are the entries of the Gram matrix. Then the corresponding, this is for general reflective lattices, doesn't have to do anything with the Covey-Andreev-Thurston theorem. What you do is you look at all cyclic products in twice the entries, and you check whether they're all in Z. So let's do another example where those entries were all integers already, so there's nothing to check. But if you take the square pyramid instead of the triangular bipyramid, you get, so the ones and zeros are the data, the combinatorial data as before, but now the Covey-Andreev-Thurston theorem returns for you 2 root 2s at some places and 3s at other places. So now there's something to check. So let's check. Let's go, what's a cyclic product? We'll go, let's say from 1 to 3, 3 to 6, 6 to 10, and 10 back to 1. So that's a cyclic product. And then you just multiply the entries at 1, 3 is there. There's a 3, 3 comma 6 is 2 root 2. Then 6 to 10 is also a 3. And then 10 back to 1 is another 2 root 2. And you see, whatever you do that stays inside the polyhedron is going to be integral. When you cross a polyhedron, you might pick up a root 2, but you have to cross back. And so you're always going to get an integer. And sometimes you'll have things like root 2 over 2. So that's what the 2g is for. Root 2 over 2 and root 3 over 2 are okay. Those are the only things that that will arise in these contexts. Okay, so that's the arithmeticity criterion. Let's just compare this to the icosahedron, dodecahedron, or what's basically the same in this case is the 5 pyramid. So pentagonal pyramid, the Covey-Andreev-Thurston theorem gives you elements that look like 2 plus root 5. And so if I go from that wall right back to where I started, I just get 2 plus root 5 squared, which is not an integer. Okay, so this is non-arithmetic. So great. If we have a polyhedron, we want to know whether it's arithmetic. We just compute this Gram matrix and check Vinberg's criterion. But wait a second, how do you actually compute the Gram matrix? Where do these numbers come from? I have to tell you a little bit more about the proof of the Covey-Andreev-Thurston. So
I'm a little bit confused. This is not the matrix of all of the cyclic products, right? You filled in some other numbers here.
So this is the matrix of all inversive products of the sphere, the circles in the cluster and co-cluster together. And then what you need to do, okay, here everything is integer, but in general.
But what was it you said you had an arc cosine, which was not 3. So what was that?
These numbers are the cosines, are the hyperbolic cosines of arc cosh of 3. So what I was saying back here is that the fact that this number is 3 is kind of weird.
Oh, I see. It's not the hyperbolic distance.
It's the cosh of the hyperbolic distance, but the hyperbolic distance turns out to be arc cosh of a whole number or an algebraic number. And so in other situations where these strange numbers, the mysterious numbers that arise from Covey-Andreev-Thurston happen to be things like 2 root 2, when you apply this criterion, which is about cyclic products through the Gram matrix, you still get integers. But in other situations, you don't. So let me just show you one more situation. We were talking about the pentagonal pyramid, and now I'm going to take the pentagonal pyramid and just add one more vertex. And this is the new Gram matrix. There's negative ones, zeros from the combinatorics, and then you have things like an 8.4, which is a root of a degree 8 polynomial. Okay, so you get really, really strange numbers arising all over the place in general polyhedra. And by the way, as I was preparing these lectures, I remembered, I have no idea if there's any control on the degree of the number fields, for example, that arise, how that grows with the combinatorial complexity of the polyhedron. So that's a separate question. So it doesn't have to grow because, as I said already, there's infinitely many that are purely arithmetic. And so there's already infinitely many that just have purely integer values here.
So is it a coincidence that they're all algebraic?
It is not a coincidence. I'm going to say it a little bit later, but it's Master rigidity. Master rigidity forces these things to all be algebraic anyway. Yeah, so they will always be algebraic. The question is this Vinberg criterion satisfied? And most of the time, the answer is no. Okay, other questions? So far, everything makes sense?
So does this mean you have an actual algorithm to compute exactly this graph matrix for any input pi?
Outstanding question. Let's get right to that. So let me tell you more about the proof of the Kobe-Andreev Thurston theorem to tell you exactly how to do this. So there are lots of different proofs. There are proofs that I really like, starting with work of Colin de Vergier, Schramm, Igor Riven, Bameka Springborn, where the idea is to realize this problem as an energy minimization problem. So you have to very cleverly cook up an energy functional. So first you just guess where the radii, where the centers are and where the radii are, just completely kind of at random, and say how close are we to having a configuration that has snapped into place. And then this energy functional you prove is convex, and that at its minimum, it realizes a solution to the problem. So then what you do is gradient descent. So you run things down, and it looks like it's getting into place. But then you're a little bit stuck because for a given polyhedron, you just numerically, you just cook up this gradient function, this energy functional. You tell your favorite software package to minimize it. It spits out 100 decimals of precision. But for Vinberg criterion, you need to know whether 2.999 is literally 3 or not. So the final step is to use Monster rigidity to know that they're all algebraic. And given that they're all algebraic, you use, this is not an LLM, this is an LLL, the algorithm that guesses a nearby algebraic number. And then you can go back and rigorously verify that that guess has exactly the orthogonality and tangential tangency property.
What's the RL?
This is the Laszlo Lenstra-Lovász algorithm that computes points and lattices. So you basically have you just guess that an algebraic number is you guess the degree, and you take your number that you have to high accuracy. You take 1 and it and its square and its cube and so on, and you find an integer, a nearby integer linear combination of those things, and that tells you what the minimum point.
Do you have any a priori bounds on the degree from
No. That was one of the questions. Yeah, I have no idea how to a priori say how bad it is, and already with 7 vertices, you're getting octets. So is it linear? Is it super exponential? I have absolutely no idea.
You don't even know if this is decidable. Could be that it's the halting problem that's encoded.
My feeling is that the halting problem is not encodable in this, but I think it's decidable. I think it's possible to prove it. I'd have to think about it. Yeah.
Say check if right.
Yeah.
What do you mean by check if right?
Okay, so you have centers and radii. You've computed them to high accuracy numerically. You guess that there's a nearby algebraic number. You compute what that algebraic number is, and then you rigorously check whether what you were trying to solve is that this circle is tangent to this circle exactly, and this circle is orthogonal to this circle exactly. So given those algebraic numbers, you can check those things.
But doesn't it give you an a priori bound on the degree because you're just solving a system of equations? It's like a couple degree equation for each. It should be like exponential.
That's probably right. It's probably exponential, but in practice, it can be much, much less than. In fact, it can be, you can have integer solutions to arbitrarily complicated things.
So when you use LLL to do this, you have to tell it what degree you think it is before you do that. Right?
There are already algorithms that will try a degree, and if it doesn't find anything good, it tries another degree. And
You just try all of them.
we're not doing this by hand. There are packages that.
Oh, sure.
Yes. You just feed it a large number of decimals and say, is there an algebraic number nearby? And it says, yeah, look, it's a solution to this degree 8 thing. Or it looks like a solution to this degree 8 thing. And then you go back and check that the tangent conditions are exactly satisfied, and then that's it. Okay, so that's how everything at the end, you get near snapping to a grid, and then you finally snap to the grid. And now you have the exact solution. Okay, does that make sense? So again, that leaves open the question of, let's go back to the main question. Now I've told you how to actually compute all of these things. So which ones are arithmetic? So again, with Nakamura, we found that the tetrahedron, octahedron, cube octahedron are, as are all of their growths. The commensurability classes, these are all going to be commensurable to Bianchi groups. So they have discriminant -1, -2, and -6. And then I had, for 2 different summers, I had RAU groups computing, getting better and better algorithms to compute these things. There are a lot of polyhedra. And they kept finding new arithmetic guys and then spending a week figuring out why that arithmetic guy was a construction of something else that they could make out of tetrahedron. Why it's a growth. So we never found anything new. And so naively, you would say, well, we haven't found, but there are so many polyhedra. I think the space of polyhedra grows so fast. It's a very naive conjecture, I would say. But we thought this was probably all of them. And then a long time went by. That's what this blank space is a lot of, just, I don't know what to do with this problem. Like the Cobian drift, right? It's this transcendental process where you're trying to find these things, and why should the answer for some cases be arithmetic and others not? And we were really stuck. And then a few years ago at an AIM meeting, I started talking about this problem again, and the key idea was to start working backwards. Wait a second. If what we're going to get is a reflective arithmetic lattice, there are very, very few of them. So this was already known to Vinberg, that he proved in the 80s that above dimension 30, there are no reflective arithmetic lattices, period. In fact, there are no hyperbolic, never mind arithmetic, there are no hyperbolic lattices above dimension 1000 or something. The highest dimension that's even known today is dimension 22, construction of Borchers using the Leech lattice. So there are very few of them. Okay, well, I'm talking about dimension 3, so that result doesn't actually help me. But there's, thanks to work by many people, Nick Poulin, McLaughlin Reed, Agel, and then Agel, Lipinski, Storm, and White, showed that in every dimension where there do exist these things, there are only finitely many maximal arithmetic reflective lattices. Great, that's still not enough for what we have to do. Remember, the image of the Cobian-Andreev-Thurston theorem is always all ideal, all right-angled. There was a classification 30 years ago by Charlow and Walhorn of what they called strongly square-free maximal arithmetic non-uniform reflective lattices. And very recently, Daniel Alcock managed to show that that's actually all of them. So wait a second. Now we can do something. Because if we know in dimension 3, they're going to be ideal, so they're going to be over Q. The vertices are ideal. These are non-uniform lattices. So you can't have if you're over a number field, they have to be co-compact. So you have non-uniform reflective lattices. The maximal ones are some tile, and the question is, can we say something about these tiles and whether they can unfold to make something that's all ideal and all right angled? Okay, does that make sense? So let's have a look at the classification. What does it look like? So here's just a piece of the classification. There's 49 total. I've shown you 7 of them. So these are some Coxeter Vinberg diagrams, if you like. Let's just have a look at one of them. So this one, so here's how to read these diagrams if you're not used to it. The nodes correspond to the walls that you're going to reflect across, and the edges connect 2 walls with multiplicity n if the dihedral angle at which those 2 walls meet is pi over n plus 2. That's just the standard way of doing this. So for example, walls 2 and 4 have no edge, and so that's multiplicity 0, and so they meet at pi over 2. They're orthogonal. Walls 2 and 4 are orthogonal. Walls 3 and 4 meet at angle pi over 4. So this is a 45, 45, 90 triangle. 2, 3, 4 is a 45, 45, 90 triangle. 1 is orthogonal to 2 and 3. Let me just show you the picture. Maybe you'll see it better. So 2, 3, and 4 are these 3 circles. 3 circles. They're circles with radius infinity. And 1 is this circle centered at the intersection of 2 and 3 that has radius twice the distance to 4 because cosine of pi over 3 is a half. Okay, so every one of these pictures actually corresponds to some configuration of circles and reflections through those configurations give rise to, in hyperbolic space, something that looks like this, a little chimney. Maybe you can see it better just coming, imagine this coming out towards you. And then out, but only the part that's outside of this hemisphere. So that's what I'm trying to illustrate there, just to have it stand straight up.
Is there a reason the labels are in the order 1, 4, 3, 2 instead of 1, 2, 3, 4?
It's because I drew these labels first. And even these go 1, 2, 4, 3 for some reason. Yeah, no, the labels, in fact, most people don't label them. They just draw the picture without labeling, but I wanted to be able to say which one's which. The labeling means nothing.
I just want to make sure there was
Yeah.
any mathematical significance to that.
Yeah, it's the multiplicity of the edges that has meaning, not the nodes. So, okay, so the question becomes, given this tile, is there some way to unfold it and get something that's all ideal and all right angled? And you start saying, well, this wall 1 is this compact wall. So that's bad, because we need all ideal edges, but it meets wall 4 at angle pi over 3. And so maybe if I take 3 copies of this thing and glue it across walls 1 and 4, that'll straighten things out, and wall 4 will have this. There's a long string of arguments about how to do this, and it turns out that when you take 48 copies of this guy, you get this shape, which is indeed all ideal and all right angled. And maybe you recognize it as the tetrahedron. So again, the tetrahedron is the blue circles. The dual of the tetrahedron is tetrahedron self-dual. That's the red circles. And if you take there's a chimney like this coming out towards you, and then outside of these 4 geodesic hemispheres, hopefully you see that's exactly what's happening here. There's this chimney going out to infinity, and then 4 right-angled hemispheres have been cut out of it to make this this picture. Okay, this is several weeks of trial and error, but
This thing would be like a group of index 48 in the tetrahedron.
correct. Yeah, and it's not the unique way to make a tetrahedron, it turns out. There are other commensurate, other maximal lattices like this, these tiles that will also fill out the tetrahedron. Okay, so let me show you one of the other ones. This is back to the classification again. Let me show you one of the other ones. So this is this is what most of them look like. Most of them don't look like the first one that I showed you. Most of them just are some horrible mess of walls and very few relations. Walls 3 and 4, the thick line between walls 3 and 4 is that they meet at angle pi over infinity. The edge multiplicity is infinity, namely 0, so they're tangent. They meet at infinity. Walls 2 and 6 also are tangent. So I didn't label them, but one of these two is walls 2 and 6, and the other pair is walls 3 and 4. That's this square cusp going up to infinity. And then there's a whole bunch of other things, and you're supposed to figure out, does this thing unfold to an all right angle, all ideal polyhedron? And let me point out a few things. So here's walls 1 and 8 that just happen to jump out at my eye. And they're both compact walls. So let's say, I don't know which one it is really, but let's say this is wall 1. So it's compact. It meets everybody at right angles. So if you think about the tiling by all of hyperbolic 3 space by this thing, in the wall through this face 1, all you'll see is more copies of face 1. And so if you're trying to get something that's all ideal, you have to get rid of that face. You have to double across that face. That face can't be part of an ideal polyhedron. And the same exact logic applies to wall 8. And let's say this is wall 8, this little guy. And wall 1 and wall 8 are disjoint. And so you have to get rid of wall 1, and you have to get rid of wall 8. And as you try to get rid of one and the other, you always get more of each. And so the group generated by reflections in walls 1 and 8 is infinite. And so there is no finite ideal cover, and this guy can't be the cover of a polyhedron. Okay, that's the easiest kind of argument. So this kind of argument kills maybe 20 of these. Then there are, so let me tell you the final, this is work in progress. There's a little T there, so hopefully we'll get this really nailed down, but it's looking very, very solid. This work in progress with Daniel Alcock, Pat Devlin, Anna Felixson, and Ian Whitehead. And you take these 49 lattices, and in this Charlotte-Walhorn-Alcock classification, 5 of them do indeed unfold to polyhedra. 2 of them unfold to a tetrahedron, 1 unfolds to a square pyramid, and there were 2 that had the same discriminant. And I'm like, what the hell are they going to unfold to? Because I only know one other thing, which is the cube octahedron. And one of them unfolded to a cube octahedron. And then the other one we were really struggling with, and it also, turns out, unfolded to the same cube octahedron. So there's just, it's really complicated, but when you get down to the bottom of it, it's the same object, just seen from, there's 2 different ways to chop up the cube octahedron and get this maximal cover. So 5 of them do unfold to polyhedra. The other 44, like I said, there's this easy argument that kills like 20 of them, and then every time you've only killed some of them but not the others, you find some other new argument, some other reason why this can't unfold to be all ideal, all right angled, and that killed another 20, and then there were 3 more that we really struggled with, and then there was the last one. And the last one is actually the very first one on the list. It's the Eisenstein Bianchi group, SL2 Z adjoint cube root of unity. And that guy we struggled with for about a year and a half. And eventually we found a very roundabout argument involving Euler characteristic and what the face configuration must be through these various walls. And once we put that one to bed, now we're confident that the rest of them are much easier. We have to write all of this up. So the conjecture is almost solved in the sense that we really wanted a complete classification. What we haven't done is the 5 that can be unfolded to polyhedra, we haven't shown that they must be unfolded to the polyhedra that we found, those seeds. So there may be other seeds. We have a lot more work to say, you know, you're forced to unfold it. If you're going to get an all ideal, all right angled guy, then you're forced into that situation. But otherwise, this really naive conjecture is looking pretty good. So stop there. Thank you.
Any questions for Alex?
There doesn't seem to be anything on the sort of the manifold side that's being really, I mean, more analytic side of this that's being reflected on the.
Yeah, the analytic side goes into the classification.
Okay.
Yeah, the classification is something like, so we, by the way, don't have a complete classification even in arithmetic 3-manifolds over Q, because the ones that are co-compact, you sort of can't even get started. And that's the only dimension where there can be non-co-compact over Q is 3-1. Once you go to 4-1, once you go to signature 4-1, if you're over Q, then you have a cusp. Then you have an isotropic vector. And so in this classification, what you do is you say, okay, suppose I have a cusp at infinity. Well, that means I must have a reflective lattice about infinity. And there's only, you know, it's like the 45, 45, 90 or 30, 60, 90. There's very few, there's a large constraint on what can happen there. And then the question becomes, what kind of quadratic form? There's some p-adic quadratic form analysis that says bounds on the discriminants of what can happen depending on what you have at infinity. And yeah, so there is some arithmetic going into that place. But then once you have this list of 49, it's really just slogging through which ones can be unfolded or not. And that turns this, you know, going backwards, instead of trying to start with the polyhedron, run this strange process and hope that you're going to see something arithmetic or not, it's sort of, we have no way of being able to say anything in that direction. That's where we were stuck for so long. But if you go backwards and say, wait a second, if they're reflective and arithmetic, they're very, very few. Finally, we have a classification. That means we can go through this classification and one by one check what's going on. And it looks like the reason we didn't find anything else is because there isn't anything else.
Are there any more questions? No, if not, then let's thank Alex again.